In our last video, we looked at the rigid body model. We expanded our particle model to the rigid body model, and what we did was we used that to take into account the energy associated with rotation, the rotational kinetic energy. And we derived that as the rotational kinetic energy was equal to 1/2 the moment of inertia times the angular velocity squared, where the moment of inertia was sort of property of the object and the axis it was rotating around, sort of described how the weight was distributed relative to that axis of rotation. Um, what we're going to do today is we're going to do an example of this and sort of show how we can use it for objects that are rolling, right? So when an object's rolling, what we know is, for this object here, if it's rolling, we know the center of mass is moving that way. That's kind of how we would have treated it in the particle model. There's some velocity at the center of the mass that's moving. But we discussed, getting the kinetic energy of particles on that object that are spinning. They're obviously moving at different speeds than the center of mass. How do we figure that out? Well, we have to use relative velocity, right? If I want to know this object, we're going to say this point is the ith little chunk of mass in this object. If I want to know the velocity of that chunk of mass relative to the center of mass, well, that's easy. If I imagine myself sitting at the center of this spinning object, it's a distance ri relative away. That velocity is just going to be that distance ri relative to the center of mass. Um, Sorry, they've been using that subscript. Our center of mass times that angular velocity. This is just that relationship we have where that tangential speed is equal to r omega. Well, if I'm at the center of mass, that's what I get for that object. But I have to also consider that the center of mass is moving at its velocity. So the velocity of that object relative to someone watching from, say, the ground standing still, we get the velocity of that ith point is equal to the velocity of the center of mass plus that velocity of that object, of that part of the object relative to its center of mass. And this is a way I can calculate the speed of that object. Um, Now, if we look at an object that's rolling, right? One of the ways, like the way we think about rolling, we discussed this a lot when we were going through friction, is it's rolling without sliding, right? The surface, the bottom of the wheel stays where it is relative to the ground and then comes off, right? So we know that the velocity at the bottom of the wheel relative to the ground is zero, sort of by definition. If it's the velocity at the bottom of the wheel must be zero because it's not sliding. It stays stationary relative to the ground when it's touching it. However, we look at the center of mass is some velocity v center of mass. The top of the wheel, well, if we look at how the wheel moves, it's going twice, it has to go faster than the center of mass because, later on, this point is going to be over here. It has to go further than the center of mass did to get there. The top is going faster. And if we look at that formula we derived on the last page, we have the center of mass plus r I omega. In this case, that r is just the radius of that wheel, right? So this ends up being the center of mass plus the radius of the wheel times omega. But we also know that this is ends up being equal to the center of mass, the velocity of the center of mass, right? Because you can kind of think of this as going on a circle like that, spinning at the same rate, or if you think of how fast, a better way to think about it might be relative to the center of mass, the bottom of the wheel is going negative r omega, so the switch, uh, that tangential speed is r omega, so the center of mass is going r omega relative to the bottom. But the point being that the velocity at the top is equal to v center of mass plus r omega, and the center of mass is equal to r omega. So we have two of those. The velocity at the top ends up being 2 times r omega, twice as fast or which is 2v center of mass, twice as fast as the center of mass is moving. This would be a lot clearer if we look at a point on the bottom of the wheel and track how it goes as it comes around to here. Well, the distance it travels between those 2 points is just one circumference of the circle, right? This wheel has gone, if you think about unrolling it, it goes all the way that far. The path that particle travels looks something like that. And it's moving, that wheel's moving at whatever the speed the center of mass is moving. So that velocity of the center of mass is equal to 1 circumference, which is 2 pi r. If it divided by however long it took, the period or the time it took to spin around once. If we look at that 2 pi over the period of rotation times r is equal to omega times r. So again, we get the velocity of the center of mass is equal to omega times r. This is really a key point we're going to have to use when we're describing how objects move or roll without slipping. It's what we'd call an equation of constraint, right? That this wheel rolling without slipping means that the wheel's constrained to move such that this is true. And why it's important is, if you remember, we're going to have rotational kinetic energy plus translational kinetic energy. And this rotational depends on an omega. This translational depends on a velocity of the center of mass. And if we're going to actually want to solve for those, we need a way to relate those. We have 2 sort of unknowns typically. And the way we can do that is through this equation that relates the velocity of the center of mass, or the speed of the center of mass, with how fast that object's spinning. So then if we want to look at the kinetic energy of a rolling object that's rolling without slipping, we have the kinetic energy of rotation. We have the translational kinetic energy, which is just the 1/2 the total mass times the velocity of the center of mass squared. And we can add those 2 together. But since we know it's rolling without slipping, we can then connect those 2. So this is where, let's just start with an example so we can see what it is. So what we have in this example is a cylinder on the top of some ramp that's up at that has some height h and is at some angle theta. The question is, let's ask, how fast is it moving when it gets to the bottom, when it gets down here, if it's rolling without slipping starting from rest? So we're familiar with sort of the concepts behind here. We know that there's we're going to ignore friction. It's rolling. It's probably extremely small. So we're just going to ignore that, which is a safe assumption, and look at conservation of mechanical energy. We have, at the start, we have some kinetic energy and some potential energy, and we know that since that's going to be conserved, we have the same total kinetic and potential energy at the end. We know that since it's a rigid body that's rolling, there's going to be some rotational kinetic energy and some translational kinetic energy. And since there's no springs or anything, all there is this change in height. All we're going to worry about is some gravitational potential energy, which is just the mgy center of mass. And at the end, we're going to have the same types of energy that we need to consider. Mgy center of mass final. Should add an F subscript to these and an initial subscript to these. So we have those types of energies is what we're going to have to think about. Now, if we look at the start, it started from rest. So those kinetic energies are going to be 0. And all we have at the start is mgy center of mass. At the end, well, it's moving now. So we have 1/2 I omega squared plus 1/2 m v center of mass squared, and again, final. And now that we're at the bottom, we can define our 0 to be the center of mass there. This is going to be 0, so it's plus 0. Now, normally, if we didn't discuss those equations of constraint we had, we're kind of sunk because we have 2 unknowns and only this one equation. However, we know that the V center of mass is equal to R omega. So we can, or equivalently, omega is equal to V center of mass divided by R. So we can make that substitution for this omega final, and we get mg y center of mass initial is equal to 1/2 I V over R center of mass final squared plus 1/2 mv center of mass final squared. Uh, we can do one more thing. This is a cylinder, so if we look at our table of moments of inertia, we know this is 1/2 total mass R squared. So we can make that substitution as well. This becomes 1/2 times that moment of inertia, 1/2 mR squared times V center of mass squared over R squared plus 1/2 mV center of mass squared. And this is all also going to be equal to that initial gravitational potential energy. And now we can see that we can solve this pretty straight away. We can just divide everything by mass, and all these masses cancel. This R squared cancels with this R squared. And what we end up left with is G y center of mass initial is equal to 1/4 times V center of mass squared plus 1/2 V center of mass squared. Or if we do this together, excuse me, this is 3/4 V center of mass squared is equal to G y center of mass initial. Or solving for V center of mass at the end, it's going to be equal to 4 divided by 3 times G. And since we started at some height H, this is just G times H, all square rooted. And, you know, I went through a lot of detail in the algebra from here down, but fairly quickly using our conservation of energy like we've done before, we can figure out the speed at the end of, at the bottom of the ramp. What's interesting is, had we not done this kinetic energy of rotation, had we just used the particle model, what we end up with is mgh is equal to 1/2 mv squared. Our old, should be familiar result by now from just the particle model. We get v is equal to 2gh all square rooted. And this is faster than that, right? What we notice is, because, you know, the fact that there is a moment of inertia, there's actually a rigid body that's spinning, and that, just the fact that it's spinning contains some of that kinetic energy, the kinetic energy of rotation. We see that there's less energy associated with its actual change in position, its translation. So when you think about that, if you have an object rolling, it's going to move slower than had it just been sliding without friction, say. And it's all because there's energy that's associated with just that rotation, you know, not even counting the fact that it's changing position, that translational kinetic energy. So consider this. I think in one of your labs, you have to go over predicting how far things launch. This is actually something you might have to take into account. You know, are there wheels spinning? Is the ball rolling? Is there an energy associated with something that you haven't been accounting for with your particle model? Anyway, hopefully this made sense. We'll go over more examples in class. If you have any questions, feel free to email me, and I will talk to you then.